All right, so we're going to go through an example. So we're given the true stress versus true strain. And it looks like this. We're given the data points. And you always have to be given what the material or what model this material follows. And so this material follows the nonlinear kinematic hardening model with a constant size of the yield surface. So when I plot sigma yield versus epsilon p, basically sigma yield versus epsilon p is sigma on 1 minus that. So you calculate the elastic strains and subtract the total strains minus the elastic strains to get the plastic strains. You'll find that there's a little bit of an elastic region up to the stress of about 360 MPa. So 360 MPa. And then this is the relationship between sigma yield and epsilon p. So what's the value that would define the size of the yield surface since it's constant? Which value?
36.
Yeah, exactly. Because the initial size is the same size all the time. And so the yield stress is always 360, and so this is the relationship between alpha and epsilon p follows this relationship. And so you can subtract whatever number. This is equal to 360 MPa to find the value of alpha. The first thing is we need to find the values of C and gamma to fit this curve. So we know now how to find this curve. You find this curve by basically drawing this one and then subtracting 360 from each value of sigma yield to get the corresponding value of alpha. So now I have data alpha versus epsilon p. So basically I have sigma on 1 versus epsilon on 1. Then I have sigma yield versus epsilon p, which is equal to epsilon on 1 minus epsilon on 1 elastic. And then alpha is equal to sigma yield minus 360. And so I have this data, and I can fit a curve with whatever tool you want. Find C and gamma, and C and gamma are equal to, happen to be equal to 2, 3, 5, 2.3, and 8.974. So these are the best material constants that would fit this curve. So now we have the material constants. We can now load the specimen in any direction, find the evolution of all the stresses and the plastic strains. So A specimen of this material is incrementally loaded in shear up to sigma on 2 from 0 to 300. Then sigma on 2 is unloaded from 300 to 0. So this is step 1. Step 2. And step 3. In step 3, now sigma on 1 is increased to 500. So from 0 to 500. I want to track what happens in that material when I do this. So I take a piece of material that follows all this material model, I shear it, develop some plastic strains, and then I unload it, and then I pull it in another direction. So I want to see how the plastic strain develops. So in step 1, initially, alpha ij equals 0. We know sigma y alpha is equal to 360. Yield surface square root of 6 sigma on 2 minus alpha on 2 squared. Now this is 0 divided by 3, but divided by 2 is equal to 360, from which sigma on 2 is equal to 207.85 MP. So the initial yield happens when sigma on 2 is equal to 207.85. Once we reach that point, the yield surface will start moving, and I'm going to start developing plastic strain according to the equations. Sigma on 2 changes from 207.85 up to 300 with increments delta sigma on 2. Accordingly, delta alpha ij will change as well. So I want to find all these, so I'm going to use the consistency condition. Partial f by partial sigma on 2, delta sigma on 2, plus partial f partial sigma to 1, delta sigma to 1, plus partial f by partial alpha ij, delta alpha ij, minus d sigma yield alpha by d epsilon p, this is 0 because constant size of the yield surface. Let's just look at what delta alpha ij looks like. Delta alpha ij is equal to C over sigma y alpha, which in this case is always constant at 360, sigma ij minus alpha ij minus gamma alpha ij epsilon p delta. So initially, all the alphas are zeros, and all the stresses are zeros, and after that, only the stresses that develop are only sigma 1, 2, and so because the only ones that will develop will be delta epsilon, delta alpha 1, 2. All the other alphas will not change because they're only functions of the sigma ij and alpha ij. Alpha ij's are initially zeros, and all the initial stresses, all the other stresses are zeros except sigma 1, 1 and sigma 1, 2. And so this term will only be non-zero for alpha 1, 2 and alpha 2, 1. The only alphas that will develop as I in shear is alpha 1, 2 and alpha 2, 1. From the above equation, delta epsilon p can be calculated. It's the only unknown. You can integrate. So delta epsilon p can be calculated. Once you have delta epsilon p, you have everything. I have delta epsilon p, therefore epsilon p delta epsilon plastic ij is equal to partial f by partial sigma ij multiplied by delta epsilon p, and delta alpha ij can also be found. And so in your notes you have a table of the integration, and the alphas, of course, epsilon p ij is equal to the sum of the deltas, and alpha ij is equal to the sum of the deltas. At the end of this loading step, the plastic strain is equal to 0.0951, and alpha 1, 2 is equal to alpha 2, 1 is equal to 92.15 MPa. And the plastic strains are also calculated. Step 2. Let's see what happens with the sigma 1 pieces, sigma minus alpha. This is equal to the square root. Now I have sigma 1, 2 are decreasing. Sigma 1, 2 decreasing up to 0. So let's see what happens at 0. This will be equal to 3 over 2. Sigma 1, 2 minus alpha 1, 2 squared plus sigma 2, 1 minus alpha 2, 1 squared. When sigma 1, 2 is between 300 and 0, sigma 1 means sigma minus alpha will be less than the 360 MPa. Therefore, unloading is occurring and no plastic strings. So as you unload, because how this model might predict even as you unload, because you might move the yield surface so much into one direction, such that when you're unloading, you're actually developing plastic strain in the opposite direction. But we just made sure that even at sigma 2, between 0 and 300, as I'm unloading, I'm always less than 360 MPa, so I'm still inside that yield surface. Step 3. Sigma 1 increases from 0 to 500. I want to find when will I hit the yield surface. I will hit the yield surface when sigma 1 means. Now, I know already that alpha 1, 2 has not changed. It's equal to alpha 2, 1. It's equal to 92.15. So yield will happen when sigma 1 means evaluating at sigma yield at sigma minus alpha minus 360, which is the sigma in alpha, is equal to 0. Sigma on 1 minus sigma 2 squared plus sigma on 1 minus sigma 3 squared plus it's sigma on 1 minus alpha on 1, which is 0, squared, plus sigma on 1 minus alpha on 1, which is 0, squared, plus 3, sigma on 2, which is 0, minus alpha on 2, squared, plus 3, sigma on 2, minus alpha on 2. Sorry, sigma to 1. Alpha 2. So this will happen at 360 when this is equal to 360. So what do you expect? Initially, the yield was 360 MPa. When will I develop yield? Because of the Bollinger effect, because of everything that we're doing here, I will develop yield when sigma on 1 is less than 360 MPa. This is what this model predicts. Because of this alpha on 2, which is 92.15, sigma on 1 at initial yield is equal to 322.7 or 684 MPa. What does this tell me? Because I have a history, because of the history of shearing the metal in sigma on 2, after unloading and then pulling the material in sigma on 1 direction, I observed a reduction in the yield in the direction of sigma on 1. Because originally the yield was 360 MPa. Now the yield has reduced to 322.684 MPa. Now sigma on 1 moves from 322 .684 up to 300, up to 500 in increments of delta sigma on 1. And accordingly, delta alpha 1, 1, delta alpha 1, 2, and delta alpha 2, 1 will change. The other alphas will not change. The only ones that will change are delta alpha 1, delta alpha true 1, and delta alpha 1 true, which is the center of the yield surface. So how will these change? Partial f by partial sigma on 1, delta sigma on 1, plus partial f by partial alpha on 1, delta alpha on 1, constant size of the yield surface. Delta alpha on 1 is equal to C sigma on 1 minus alpha on 1 divided by sigma yield alpha, which is 360, minus gamma alpha on 1 multiplied by delta epsilon p. Delta epsilon to 1 is equal to C sigma to 1, which is 0, minus alpha to 1 minus gamma alpha to 1 divided by 360 delta epsilon p. Delta alpha on 2 is equal to C sigma on 2 minus alpha on 2. This is 0. When you take those three and plug them here, you get one equation in delta epsilon p. You calculate delta epsilon p. When you calculate delta epsilon p, you have everything. So you can now integrate this. And once you have delta epsilon p, once delta epsilon p is calculated, the plastic strains developed and the location and the backstress tensor can be calculated. Epsilon p ij is equal to partial f by partial sigma ij multiplied by delta epsilon p and delta alpha ij is equal to C over sigma yield alpha, sigma ij minus alpha ij minus gamma alpha ij multiplied by delta epsilon. Yes?
We should increase the incremental form or not?
Yes.
We should derive an equation to it.
No, just increase in incremental form. You might not be able to explicitly integrate this. There are many ways of integrating this, but the easiest way is just, when the equations become very complicated, just plug in numbers. Or use a numerical, you can use Mathematica, but just if you're in an exam or even for the assignment, just use an Excel spreadsheet. Okay. In all of the above, partial f by partial sigma ij is equal to negative partial f by partial alpha ij is equal to 3 over 2 Sij minus alpha ij deviatoric divided by sigma 1 mesus evaluated at sigma minus alpha. So this is going to complicate your equations and you will not be able to explicitly integrated. And in the here in the example in the notes, I integrated this numerically just by yeah. Now, very important when you're integrating numerically, you're evaluating those values at the previous increment or at the current increment, and then you increase. When you increase delta epsilon p, that means alpha 1 and alpha 2 1 and alpha 1 2 have changed, and they appear inside these equations. So as you integrate, you just apply the new numbers. Every increment, it's a new number. For your assignment, you basically have to repeat. You have to do this for another example, but exactly follow the same steps. The difference is you have sigma on 1. We apply sigma on 1 up to 1.5 plastic strain, and then unload, and then apply sigma 2. Do you guys have any questions? So this is it for the term. You guys learned a lot. I hope there's a lot of information in this course. Linear, large deformation elasticity, small deformation elasticity, large deformation elasticity, incremental von Mises plasticity, isotropic hardening, kinematic hardening. So this will serve for any graduate students. This will serve as a really strong basis for many of the mechanics, for many of the research in mechanics. So if you stay in academia, sooner or later, you're going to come across many of the things that we talked about in this course. Whether it's linear algebra, whether it's hyperelastic materials, von Mises plasticity, incremental plasticity, fitting curves to material models, of course linear elasticity. So you're going to see a lot of the information that you saw in this course if you stay in academia. If you don't stay in academia and you prefer to make more money and you go out to the field, that you might not directly see the application of everything that you learned here, but every course that you take, even however abstract it is, it teaches you something, and you are going to be using it in some form or another. You might not. You might use it by, you have a set of data and you're fitting a curve and you remember that this is how you fit a curve. Or what's a material model, or what's a linear elastic. The relationship between the stress and the strain is direct. What does it mean that it's directly proportional? What's the von Mises stress? So you will, even in the field, unless you're just, even if you're a manager, just doing some, if you're just doing some management, you might have to do some numerical integration of some sort. So every course that you learn, you get something out of it, but it's not, it stays in the back of your head and you use it, but you don't know when or how you're using it. So I realize that there's a lot of information in this course, but I promise you, you're going to use a lot of these things either implicitly or explicitly in your future. So that's it, and we'll see you guys. If you have any questions, let me know. Next week, or before next week, if you have any questions about the course, you can set up a meeting and come and meet me in the office. I can go through any of the materials that we covered. And for the next assignment, just drop it off, slide it underneath my door if I'm not in my office, or email it to me if you prefer. All right, that's it.